Today, our speaker is David Galvin from Notre Dame and is going to talk about independent set permutations and matching permutations. Go ahead when you're ready.
So I'm ready. Thanks very much for the invitation or for the introduction, and somebody please pass on my thanks to Drew for the invitation. So I want to talk about some work that I did over last summer with Katie Hirey and Kyle Weingartner, who are both undergraduates here at Notre Dame, and Taylor Ball, who's a graduate student here. Before I start, I want to say that right now, of course, physically, I'm in South Bend. However, and maybe next year it will be actually going to Carolina physically. So onto the math. So the main players in this talk are the matching sequence and the independent set sequence of a graph. So let me just remind you with this small graph on 6 vertices as an example. The independent set sequence has as its kth term the number of independent sets of size k. So here, for example, is one of the 9 independent sets of size 3 in this graph. The matching sequence has as its kth term the number of matchings or independent sets of edges with of size k. So here with the 2 red edges, for example, is one of the 6 matchings of size 2. So you'll notice about these 2 sequences that they share a common structural property, one that very, very many combinatorial sequences share, which is that they're unimodal. They both rise to a peak monotonely and then fall away from the peak monotonely. So for my purposes, when I say that a sequence is unimodal, I'm going to mean a strict unimodality, that the sequence rises strictly monotonely to a unique peak and then falls away strictly monotonely, except that it might well be that that at the mode there are 2 values. But other than this possibility of 2 of the terms being equal, the sequence is strictly increasing on one side and strictly decreasing on the other side. So you might look at these 2 examples and wonder, well, is this just dumb luck? Was this just a consequence of the particular example I picked, or is there some general phenomenon here? And for the matching sequence, the answer is yes. It follows from the seminal theorem of Heilman and Lieb that says that the generating polynomial of the matching sequence, even for an arbitrary weighted graph, has all real roots. It follows that the sequence is not just unimodal, but actually log concave. On the other hand, for the independent set that I gave, it actually turned out just to be dumb luck, that the independent set sequence of that graph was unimodal. Wilf in the mid-1980s wondered whether the independent set sequence was always unimodal, just as the matching sequence is. And Alavi, Malde, Schwenk, and Erdős set about trying to demonstrate that. But very quickly, they discovered that it's not going to be possible to, because there are plenty of examples of graphs whose independent set sequence is not unimodal. Probably the simplest example that I know is this example here, which has a planet with 37 vertices, and there are 3 K4s orbiting around the planet. And the planets, the satellites are connected to the planet with complete bipartite graphs. So it's a very easy count that this has 1 independent set of size 0. It has 49 vertices. It has 48 independent sets of size 2, because of course, to get an independent set of size 2, you have to pick satellites and pick 1 vertex from each of the 2. So that gives you 3 times 16 or 48. But it has 64 independent sets of size 3, because you pick 1 vertex independently from each of the 3 satellites. So the independent set sequence is not always unimodal. And when Galvin, Molde, Schwenk, and Erdős realized this with an example very similar to this, they asked themselves a different question to Wolff's question. They asked, how far from unimodal can the independent set sequence of a graph actually be? So this is a slightly vague question. They put a very precise measure on how far from unimodal is a sequence. And that was a process of converting a sequence into a permutation. So let me explain that, that correspondence now. So if I give you a sequence A1 up to AM, you can convert that, or you can associate with that a permutation of the symbols 1 up to M by simply ordering the sequence in an increasing way, or at least in a non-decreasing way, and then just read off the indices. And reading off the indices will give you a permutation in one-line notation. So for example, if I take this sequence 2, 3, 5, 2, the two smallest terms are the first and the fourth. So if I order these terms in a non-decreasing way, I either start with the first followed by the fourth, or I start with the fourth followed by the first. But then I must put the second because that's the next smallest, and then I must end with the third because that's the largest. So actually, if a sequence has duplicate elements, then it might not have a unique permutation associated with it, but there'll always be a permutation associated with the sequence in this way. Now, going back to the unimodal sequences, you can fairly quickly see that there is a severe restriction on the collection of permutations that could possibly be associated with a unimodal sequence. Actually, there's only 2 to the power m-1 possible sequences that can be associated with a unimodal sequence of m terms. And the reason for that is, well, first of all, you have to identify what the mode of the sequence is. That's some number k. And that comes right at the end of your permutation in one-line notation. But then you have to fit the symbols 1 up to k-1. And because they all come before k, they have to appear in increasing order in the permutation. So you just have to select the k-1 locations from among the first m-1 for the numbers 1 through k-1. And once you've selected the locations, then you have the, you know exactly how they must be put in. But that completely determines the permutation in one-line notation, because the symbols m down to k+1 must appear in that order. They must appear in decreasing order. And so all you need to do is specify the location of the symbols 1 through k-1, that's m-1 through choose k-1 choices, and sum that over all choices of k, all choices of the mode. That leaves you with 2 to the m-1, which is very much smaller than m factorial. So unimodal sequences give rise to a very restricted collection of permutations. And Galvin, Molde, Schwenk, and Erdős discovered that for the independent set sequence, the situation is very, very different. They discovered that actually every permutation can be realized in this association. So specifically, if you give me a number m, and you give me a permutation of 1 up to m, then I can find a graph whose largest independent set has size m, such that if you order the independent set sequence in non-decreasing order and read off the indices, then exactly you will read off the permutation pi. So in a sense, the independent set sequence is completely unconstrained in terms of rises and falls. Very, very different behavior from the superficially similar matching sequence. So in this paper from 1987, they left quite a number of questions open. And one of them was an extremal question. So they asked, okay, every permutation can be realized, but how large a graph is needed to realize all the different permutations? So specifically, what's the smallest, say, f of m, so that every permutation of 1 up to m can be realized by some graph with at most f of m vertices. Now, of course, they gave a construction for any particular permutation. So you just have to look at their construction to get an upper bound on this, this quantity f of m. They had a pretty strong suspicion that their construction was wasteful. And so they didn't even actually bother counting the number of vertices in their construction in the worst case. They just gave a rough back of the envelope calculation. And what they showed was that you can get away with something on the order of m to the power 2m vertices. With m to the power 2m vertices, you have enough room to generate every permutation on m vertices, on every permutation on m symbols. Now, they speculated that this maybe isn't too ridiculous an upper bound, and that in fact, a lower bound of m to the power m should be obtainable. But this was speculation based on, again, based on some back of the envelope calculations. They didn't really formulate it as a conjecture. So with Taylor and Kyle and Katie over the summer research project for some of the undergraduates, we dived into this question and made some inroads on it. So the first, there's two basic results that I want to talk about today: upper bound and lower bound. So I think I'll start with the lower bound. So we were able to verify that this speculation that you need at least m to the power m vertices really is correct. And specifically, what I'm going to show is that if you have largest independent set size m, and you would like to have at least as many independent sets of size m as you have independent sets of size m minus 1, then you're going to need a very large number of independent sets of size m. You're going to need at least m to the power m independent sets of size m. And this does it because think about a permutation that puts m minus 1 in front of m and then has 1 further on. Well, because m minus 1 is being put in front of, because m is being put in front of m minus 1, the number of independent sets of size m has to be at least as large as the number of size m minus 1, which means there has to be at least m to the power m independent sets of size m. But the number of independent sets of size 1 is just the number of vertices. So you will need at least m to the power m vertices if you want to put 1 later in the permutation. So proving this result about this inequality forcing a large number of independent sets of size m would be enough to give the lower bound that Galvin, Maldish, Rankin, Erdős speculated. Now, we have a proof of this. We had an original proof of this that was in the paper when we submitted it, and it used some fairly heavyweight machinery. So we combined actually, no, I'm getting a little bit ahead of myself. So let me pause for a second. And before I say a little bit about the proof, let me just dive into a little bit why we would expect this condition to hold. So think about the empty graph, m vertices with no edges. That has, of course, 1 independent set of size m, but it has a lot of independent sets of size m minus 1. It has m of them. Just delete 1 vertex. You have m ways to do that. If you want to make the number of independent sets of size m grow to be above the number of independent sets of size m minus 1, you have to work quite hard, because each time you add a new independent set of size m, of course, that introduces a whole bunch of new independent sets of size m minus 1, all the subsets. So you need to have a lot of overlap between the independent sets of size m minus 1 in order to push the count of independent sets of size m higher than that of size m minus 1. And if you play around for a little bit, you'll come up pretty quickly with the construction of the Turan graph with m, not the Turan graph, the complement of the Turan graph. The disjoint union of m complete graphs on m vertices. This has m to the power m independent sets of size m, and it also has m to the power m independent sets of size m minus 1. There's m choices for which one of the km's you ignore, and then you have m to the power m minus 1 for what you have left, and that multiplies out to m to the m. So it seems like you need to push all the way up to something like this graph, copies of Km, in order to force number of independent sets of size m to beat the number of independent sets of size m minus 1. And that's what leads to the speculation that is now a theorem, that if you have the number of independent sets of size m at least as large as m minus 1, then number of independent sets of size m actually has to be quite large, at least m to the m. And I'm going to sketch a proof of that in a moment, but I'll sketch a proof of the contrapositive. So let me just state the contrapositive. If the number of independent sets of size m is too small, then the number of independent sets of size m minus 1 wins over the number of size m. Now going back to what I jumped ahead of myself on a few moments ago, our original proof of this uses some fairly heavyweight machinery. So we use two results. One is from Frankel, Furedi, and Kalai from 1988, so just a year after this question was raised. They proved a variant of the Kruskal-Katona theorem on shadows of set systems, but for balanced or colored set systems. So you think about a set system where the ground set has been partitioned into a bunch of classes, and your sets must have one element from each class. So you are very, very far from being something which could be extremized by as an initial segment of the Colex graph. And they proved tight bounds on the sizes of shadows for these kinds of balanced set systems. And then in 2008, Fromader proved a result concerning the independent set sequence of a graph. He proved that the independent set sequence is always realizable as the face vector of some balanced simplicial complex. Now, balanced simplicial complex is precisely the balanced set system of Frankel, Furedi, and Kalai. So these two results work together perfectly to prove this theorem, although it requires developing a little bit of background on simplicial complexes and flag complexes and Kruskal-Katona for balanced set systems. And I wouldn't want to talk about it if I didn't have to. And it turns out I don't have to, because we waited an extraordinarily long time for the paper to be refereed. And while we waited, we discovered that there's a much, 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 much simpler proof of this lower bound of m to the power m. And it passes through a very nice inequality related to the independent set sequence of a graph that was proven just a year after Alavi et al. Made their speculation. So this is a theorem of, actually not a year, 5 years. This is a theorem of Fischer and Ryan. So they showed that if a graph has largest independent set size m, then okay, maybe the independent set sequence can be quite crazy in terms of its rises and its falls. But if you scale it appropriately, then it becomes very, very well behaved. They referred to this theorem as bringing order into the chaos of the independent set sequence. The specific scaling is you take each count of independent sets of size k and scale it by m choose k, and then take the kth root of that. And they proved that this is a monotone decreasing sequence for all graphs. So no crazy behavior if you do this rescaling. And it turns out that this is exactly the statement that's right at the top of the slide. And you don't need all of these inequalities, you just need the last inequality. So if you translate the last inequality, well, m choose m minus 1 is just m choose m is 1. And so the last inequality translates simply into m to the m times number of independent sets of size m to the power m minus 1 is at most number of independent sets of size m minus 1 to the power m. And if you happen to know that the number of independent sets of size m is smaller than m to the power m, then just replace this m to the power m with one more copy of number of independent sets of size m, and immediately this simply says that there are more independent sets of size m minus 1 than of size m. So all our hard work understanding balanced set systems and flag complexes turned out to be, well, turned out to be very valuable because these are two very, very nice results, but turned out not to be needed for the paper because the lower bound actually follows directly in one line from this result of Fischer and Ryan. So that's a lower bound on this parameter f of m. And for the bulk of the rest of the talk, I want to focus on the upper bound. So remember that the construction that was given in 1987 gave roughly m to the power 2m vertices is what you need. And it turns out this is, as they had believed, this is somewhat wasteful because actually we can prove an upper bound of m to the power m. So in fact, this parameter is exactly m to the power m. So you'll probably expect that what I'm going to do is I'm going to try and argue that there is some worst case permutation. There is some hardest to reach permutation. And then I'm going to demonstrate that that hardest to reach permutation really does need m to the power of m vertices to reach it. But in fact, I'm not going to do that. What I'm going to do is I'm going to describe for you the construction of a quite extraordinary, or at least to my mind, quite extraordinary graph, a graph which has its independent set sequence constant. So I'm going to show you that for every m, there is a graph on m to the power m vertices with independence number m, and all terms in the independent set sequence have size m to the power m. So there's m to the power of m vertices, there's m to the power of m non-edges, there's m to the power of m independent sets of size 3, and so on. Or in the complement, there's m to the power m cliques of every size k, as k goes from 1 up to m. So this single graph on m to the power m actually realizes simultaneously every permutation of 1 up to m. And since we know that 1 up to m to the power of m is needed, then we're done. We have determined the precise value of this this largest number of vertices that's needed. So what I'm going to do to describe this construction is I'm going to take you through it in some simple cases, m equals 1, m equals 2, m equals 3, and we'll start seeing a certain pattern emerging. So for m equals 1, I am targeting the sequence that has one term in it, and the one term is 1. And that's easy. I just take a single vertex. Okay, no problem there. For for m equals 2, I'm looking for a graph that has maximum independent set size 2. It has 4 vertices and it has 4 non-edges. Well, there's the graph. Just take the disjoint union of 2 edges. Okay, no problem so far. And I'm an optimistic person, so I see a pattern here. So of course, the next thing I'm going to try for m equals 3 is 3 disjoint triangles. And I'm good because that has 27 independent sets of size 3. It has 27 independent sets of size 2. Unfortunately, it only has 9 independent sets of size 1. But I can fix that. I can take this construction and I can join to it 3 copies I can join to it a copy of K18. And that is going to not change the number of independent sets of size 2 or of size 3, but it is going to add 18 more independent sets of size 1, which will bring me up to the constant sequence 27, 27, 27. So I'm going to be using the join operation a lot in this construction. So let me just be explicit about it. The join G plus H of 2 graphs just takes copies of the graphs and adds all possible edges in between. And in terms of independent sets, what's nice about the join is that the independent set sequence is additive. The number of independent sets of size k in the join of G and H is just the sum, independent sets of size k in G plus independent sets of size k in H. Because I put this complete bipartite graph between the two of them, I can take an independent set that straddles both sides. So I either take completely from one side or I take completely from the other side. And of course, if I do this iteratively and just mutually join together a whole bunch of graphs, then I continue to have this additivity property. So now I can take the idea that was elucidated for k equals 3, and I'll try to make it work for k equals 4. And that already shows all the ideas that are needed for the general construction. So I start with 4 copies of K4. And here is its independent set sequence. Numerically, it's this. Notice that I have 256 independent sets of size 3 and also 256 independent sets of size 4. That's my target. I fall short in the number of independent sets of size 1 and 2. Here's the shortfall. I need to get 240 more of size 1, and I need to get 160 more of size 2. Now here's the thing to notice about 160. It's a perfect multiple of 16. And 16 is the number of independent sets of size 2 in 2 copies of K4. Actually, the independent set sequence of 2 copies of K4 is 8 and 16. So let me just join one after the other 10 copies of this gadget. And that will add 160 independent sets of size 2 and 80 independent sets of size 1. And that will bring me up to this sequence here that starts with 96, but then is always 256. So I fixed the number of independent sets of size 2 without damaging the number of size 3 or the number of size 4. And I still have room to play with. I can just join in some large complete graph to bring up this 96 up to 256. I guess I just add in another, join in a complete graph on 160 vertices. So this is the entire construction. And let me just say it, just so that I have said it, let me say it in the general case. For arbitrary m, you just start with m copies of km. And this gives you some independent set sequence. And the thing to notice about this independent set sequence is that it's increasing. That's easy to check. The last 2 terms are correct. They're both m to the power m. And it falls short on the antepenultimate term. But the antepenultimate term is an integer multiple of m to the power m minus 2. Which means I can fix the antepenultimate term by adding enough copies of km minus 2. So I just repeatedly join m minus 2 copies of km, that's what I meant to say just now, and that will fix the antepenultimate term. Now, of course, there's something I have to be worried about. By adding a whole bunch of independent sets of size m minus 2, I also add independent sets of size m minus 3, m minus 4, etc. And the thing I have to worry about is, what if this number of independent sets of a smaller size suddenly becomes too large, jumps over m to the power m? So the thing I have to keep track of is that as I do this fixing operation, I continue to have an increasing sequence until it plateaus out at the m to the power m. So that's some easy algebra, that this new independent set sequence is still increasing. The independent set sequence of this gadget is increasing, and you're adding an increasing sequence to an increasing sequence to give you an increasing sequence. Now the last 3 terms are m to the power m, and now we have to deal with the pre-antepenultimate term. But that's an integer multiple of m to the power m minus 3. This is another thing you have to keep track of in the algebra, that as you run down fixing the terms one by one, constantly what you have to deal with is an integer multiple of m to the power of whatever index you're currently working with. So now I just join repeatedly copies of m minus 3 copies of km, and I fix the pre-antepenultimate term. And I just keep doing that all the way down until I fixed the entire m terms. Now what I mean by the etc. here is that I deal with the pro-pre-antepenultimate term, and then I deal with the supra-pro-pre-antepenultimate term. And I can't go any further than that, because remarkably, the English language does not have a single word to represent the 7th from last term of a sequence. So if you want to play a fun parlor game, invent what are the next seventh from last, eighth from last, ninth from last, and so on. There's a need in the English language for these words. Supra, pro, pre, antepenultimate has actually been used on a number of occasions. Okay, so that finishes the discussion of the independent set sequence. We've just shown that m to the power m is precisely the worst case, and it's enough. It's enough actually for, it's enough for every permutation, and there are some permutations for which it really is needed. It might be argued that the question I've just answered is not really in the spirit of what Alave, Malde, Schwenk, and Erdős wanted to ask. They didn't ask this question, but they probably intended to ask not how many vertices are needed to realize pi if you allow inequalities, but what if you want a permutation to be realized uniquely? What change does that make to the problem? I don't know the answer. Things get significantly more complicated. Now, we can say something about this problem. So what we were able to say was, about the natural generalization of it simply to weak orders. So you give me a weak order on M, meaning you say who are the bunch of people who are tied for last, who are the bunch of people who are tied for second from last, and so on. I can give you a graph whose sorted independent set sequence realizes that weak order. All the guys who are at the bottom of the weak order are tied at the bottom of the independent set sequence, and so on. And okay, I can't do it in m to the power m vertices, but I can do it in m to the power m plus 2 vertices. So just a little bit bigger than m to the power m. And I can show that some weak orders require at least m to the power m plus m minus 1. So there's a gap here, but it's a much smaller gap than the gap between m to the power 2m and m to the power m, but still there is a gap. I won't say anything about the details of the proof of this theorem, but I'll just say that the key object that's needed for the proof of this theorem is, can you find a graph whose independent set sequence is constant, except at the kth position where it jumps above the constant by a certain fixed amount. And it should be for every position the same fixed amount. So basically the independent set sequences become a whole bunch of shifted Kronecker delta functions. And if you can achieve a construction like this, then you can just do linear algebra using the fact that the join of two graphs adds the independent set sequence. So you can just do linear algebra with these sequences to achieve any weak order that you want. And you don't have to go very far. You only have to go up to m to the power m minus 2 vertices. The construction that I showed you for m to the power m, it was pretty easy. It was not the first construction we found, not the second, not the third. Probably it was the fourth. They were getting easier all the time. And the proof that it works is particularly easy. However, for this construction, where you want to be constant everywhere, but you just want the kth guy to hop up by a certain fixed amount, you have to be much, much, much more careful about how these tail sequences are rising up to fit the gaps. Because at some point you have to go over the target of m to the power m. And then you really have to be careful about what's happening to the number of independent set sequences, number of independent sets of smaller sizes. So fortunately, we had a little bit of work to do to prove this theorem. So on this topic, there's still quite a few open questions, and I want to advertise my favorite open question. And over the years, I've had a couple of favorite open questions, and I'm very pleased that all but one of them so far has been resolved by other smarter people. So I'm hoping that this will be the next one. So every permutation is the independent set permutation of some graph. But if you restrict your family of graphs then maybe you get very severe restrictions on the sort of permutations that can arise. So for example, Hamadoun showed that claw-free graphs must have unimodal independent set sequences. Actually, we now know more. Chudnovsky and Seymour showed they must have real-rooted independence polynomials. And so that means that the independent set sequences associated with claw-free graphs, they're going to be at most the 2 to the power m minus 1 unimodal permutations. Another family of graphs that has received some attention with relation to this question of which permutations can be associated and what's the shape of the sequence is the family of trees. This is a very fundamental, very basic family of graphs. And Alave, Malde, Schwenk, and Erdős asked, is it true that the independent set sequence of every tree is unimodal? The path has unimodal independent set sequence. The star has unimodal independent set sequence. They somehow are the two extremal trees. So it seems not unreasonable to suggest that everything in between also gives you a unimodal independent set sequence. Despite a lot of papers at this point, this is really wide open. There's a whole bunch of papers giving families of trees that have unimodal independent set sequences, but these are only little old proportion of all possible trees. The best general result is due to Levin and Mandrescu in 2006. They showed that for every tree, the last 1/3 of the sequence is definitely decreasing. And that at least tells you that you can't have wild roller coaster behavior for the independent set sequence of a tree. Recently, with my postdoc, Abdul Basit, we asked what we thought was an innocuous enough looking question. Suppose you just do this for the random tree. You take the random uniform labeled tree. Is it true that almost surely it has a unimodal independent set sequence? And we discovered that because the variance of the number of independent sets of a fixed size is very, very large, much, much larger than the square of the expectation, it's very, very difficult to get concentration inequalities for the number of independent sets in a random tree. And so it actually turned out to be very, very slippery to try and tackle this seemingly simple question. We were able to make some progress. So we showed that almost surely the random labeled tree, its independent set sequence is increasing for its first 49%, and it's decreasing for its last 38%. But there's this gap in the middle between, what is it, between 0.49 along and maybe it's 0.62 along, something like that. Around the same time that we were working on this problem, Steve Heilman, who knows far more concentration inequalities than we know, was working on it, and he got very similar bounds. He also had a gap in the center. One could also ask a whole family of questions. Fix your favorite family of graphs, the family of trees, the family of bipartite graphs, triangle-free graphs, and ask, does putting this structural condition on your graph really substantially change the number of permutations that can be associated? Is there some kind of a Stanley Wilf or Marcus Tardash condition going on that as soon as you put some kind of a structural condition, the number of things you can realize drops from super exponential down to exponential? I suspect that is true, but don't really have any thoughts on how to tackle this. So in the last little portion of this talk, I want to address the second word, or rather the last word that appears in my abbreviated title down here on the bottom, which is matchings. And apologies to Laszlo and Eva. You've heard me talking about this part of the talk before, I think in somewhere in Florida, let's leave it at that, somewhere in Florida, in Tallahassee. So Alave, Malde, Schwenk, and Erdős also considered the matching sequence of a graph. And they made this observation that since the sequence is unimodal, there can be at most 2 to the power n minus 1 permutations arising from a graph who has largest matching of size n. But they wondered, can actually all these 2 to the power n minus 1 unimodal permutations actually be realized? Or are there even more restrictions on the matching sequence of a graph? And we discovered that, sure enough, there are some more restrictions on the matching sequence. And I'm not going to say a whole lot about this. I will prove one very, very simple lemma, and then I will say what the more general statement is. So here is a restriction. If you have a large matching, let's say you have a matching of size at least 4, then the number of matchings of size 2 must beat the number of matchings of size 1. So in particular, this means that the all decreasing permutation from 4 down to 3, down to 2, down to 1 is not realizable. You must have 2 appearing after 1 if n is at least 4. And this is a very simple proof by induction on the number of edges. If you have 4 edges, then you're just looking at 4 disjoint edges. And then you can just easily count that the number of matchings of size 2 is 6, the number of matchings of size 1 is 4. If you have more than 4 edges and you have a matching of size 4, then just pick an edge which is outside the matching and consider the graph obtained by deleting that edge and the graph obtained by deleting the 2 vertices that comprise that edge. Now there's the basic relation that the number of matchings of size k in any graph is the number of matchings of size k when you delete an edge plus the number of matchings of size k minus 1 when you delete the edge and all the edge and the 2 vertices of that edge. Do you include the edge or do you not include the edge? Now G1 has lost an edge, but it still has a matching of size 4 because we deleted an edge outside a maximal matching. And so we can apply the induction hypothesis on this term. And we know how many matchings of size 1 are in the graph obtained by am I saying this right? I feel like maybe I'm not saying this right. So I think all I'm saying here actually is that when you delete an edge, you can apply induction. I think I was just transposing in my mind the 2 and the 1 down here. I guess I should have maybe I should have used 2 different numerical systems. When you delete an edge by induction, the number of matchings of size 2 in G1 is still bigger than the number of matchings of size 1 in G1. And when you delete the vertex, well, because you started with a matching of size 4 and you delete 2 vertices, the worst you can do is kill 2 of those 4 edges. So you still have 2 left. And this is bigger than the number of matchings of size 1 in G. So this is although I botched it, it's still a very easy inductive proof. And at least it shows that there are some restrictions on the matching sequence, other than just that it's a unimodal sequence. But actually, this is just the tip of an iceberg. This is just the base case of a more general double induction. And the more general restriction we were able to discover, it's basically conveyed in this picture down here. If you have a matching of size n, and you fix k between 0 and n over 2, then the number of matchings of size L always beats the number of matchings of size k, as long as L is between k and n minus k. So you have this whole collection of indices that are bigger than k but smaller than n minus k, and the number of matchings of that size must be bigger than the number of matchings of size k. And the proof of this is it's a double induction. And the base case of the induction is the special case that I just made a Hames of on the previous slide. So this puts substantial restrictions on the matching sequence of a graph. So one thing it immediately says is that the mode of the matching sequence must be at least n over 2, which is already not an entirely obvious fact, that you take the matching sequence of an arbitrary graph, its mode must be at least halfway along, at least nu over 2, where nu is the size of the largest matching. And that immediately says that at most half of the unimodal permutations can possibly be realized. But actually, we can delve much deeper into this condition here. And it's a combinatorial problem to count how many permutations are compatible with this condition. And it never ceases to amaze me what sequences appear in the online encyclopedia. The sequence of permutations that are compatible with this restriction is A001405, and one can come up with recurrence relations and formulae for it and discover that it's very closely related to Catalan numbers, and the total number of permutations is little o of 2 to the power n. It's 2 to the power n over constant times square root n. And in fact, this is the specific question that was asked by Alave et al. Is the number of matching permutations vanishingly small compared to 2 to the power n? And we were able to say, yes, indeed it is. This still leaves a nice number of questions. And I think 21 out of 22, that means that I guess what I'm about to say is my last slide. And it's going to be just some of the questions that are left from this work. What is the correct rate of growth of the number of matching permutations? Is it really something like 2 to the n scaled by some polynomial factor, or is it even significantly smaller? Of course, the more stringent question would be simply to characterize which permutations of 1 up to n can actually arise, which of the unimodal permutations are allowed to arise. And then another interesting question, which when we asked it, we thought was really simple, but we've now started to look at it and have made no progress on it. Okay, I've told you that n down to n minus 1, I think there's a typo there, down to n minus 2, down to 3, down to 2, down to 1. This is a unimodal permutation, and it's not a matching permutation. Now, we were worried for a moment when we demonstrated this that maybe our proof had nothing to do with matching sequence. Maybe it only had to do with the Heilman and Lieb result, that the matching polynomial has all real roots. But no, because you can find a polynomial with all real roots whose coefficient sequence, when you sort it in non-decreasing order, induces this permutation here, n minus 1, down to 3, down to 2, down to 1. So our result about matching polynomials really is fundamentally using something about the matching. It's not just using that the matching polynomial has all real roots. So it might be interesting to know which unimodal permutations can possibly arise from the family of real rooted polynomials. And as I say, we're thinking about that at the moment, but it's proving surprisingly slippery. So I think with that, I will I'll call a halt to this part of the proceedings and say thank you very much for your attention. I see applause coming from.
Thanks very much. Yeah, we can thank the speaker.
Okay, now I hear applause too. And if anyone has any questions, do please. If anyone has any ideas, do please tell me.
Well, regarding this last question, so do you know that you can't get all of the unimodal permutations from the real rooted?
We haven't yet come up with an example of a permutation that can't be realized. So we've tried a number of obvious seeming constructions and or obvious seeming sort of extremal permutations, and we have not been able to show that that one of them can't be achieved. So it may well be that all of them can be achieved, but I don't have any sense actually.
Kind of amazing.
question that we're currently thinking about that that we haven't answered is, suppose instead of thinking about arbitrary real-rooted polynomials, you just think about 1 plus rx to the power n, where r is a single parameter. When r is really, 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 really small, you get the this permutation, the all decreasing permutation. When r is really, really, really large, you get the all increasing permutation. Which permutations arrive in between the two? And we have a very good sense. We know exactly how many there are, but we can't actually prove it. And the what it comes down to is a numerical question concerning the binomial distribution. So let me tell you the numerical question concerning the binomial distribution. Let's think about the binomial distribution with n trials and success probability p. Now, if p is 0, there are a lot of possible outcomes that all have the same probability. Actually, 1 through n all have the same probability, which happens to be 0. If p is equal to 1, then there are a lot of outcomes that all have the same probability. All of 1 through n have probability 1. If p is a half, then there are lots of pairs of outcomes that have the same probability. 1 and n minus 1, 2 and n minus 2, 3 and n minus 3. I'm just talking about the symmetry of the binomial coefficients here. Okay, so forget about 0, 1 and a half. Those are outliers. Do a binomial experiment with n trials and probability p of success, where p is different from 0, 1 and a half. It's certainly possible that there are two values, k and l, such that the probability of k successes is equal to the probability of L successes. Is it possible that there's a second pair that also has a coincidence? We believe not, and Mathematica tells me that there isn't up to n equals 10,000. But we can't prove it. We can't prove that you cannot find pairs KL and K prime L prime such that the probability of K successes equals the probability of L successes, and the probability of K prime successes equals the probability of L prime successes. And it feels like this might be a question related to divisibility of binomial coefficients, which would mean it's utterly impossible.
Huh, that's. And I actually had another question about the, so just to be clear, the your Stanley Wilf / Marcus Tardosh type conjecture, this is that if you forbid some subgraph that gives you an exponential upper bound.
Right, the number of possible permutations will drop from m factorial down to exponential.
And so your example, this join of all that stuff that gets you equal, the vector where they're all equal, that doesn't have any forbidden subgraphs?
It has, well, I guess you have to be careful. It has, its largest clique has size m. So of course you can forbid a clique on m+1 vertices, and the construction works perfectly.
Yeah.
And it has largest independent set also of size m. So again, you can forbid an independent set of size m+1. And so I guess I'm talking about forbidding some small constant size subgraph.
Yeah.
Like just for concreteness, triangle free.
That's a really nice question too. Thanks. Anybody else, other questions?
Well, thanks again for the invitation. I always love to travel, and this was a nice trip.
Oh, thanks very much. Enjoyed the talk.
Thanks, Tom. Thanks, everyone.
Thanks.
Bye-bye.